In this section, we're going to be talking about limits again, but this time, instead of limits at a specific point, we'll be talking about limits as x approaches positive or negative infinity, as well as how that converts over to looking at different sequences. To begin, let's look at this function here. F of x equals x plus 1 over 2x. I've got it graphed, and we can see that as x approaches positive infinity, so as this red curve goes to the right, the y value of this, f of x, is going to approach 1/2. And we see the same thing as x approaches negative infinity. It will also approach 1/2, albeit on the right side, it'll approach 1/2 from positive, from positive side, and then from here, it'll approach from the negative side. So let's look at the definition of then limits at infinity. If f is a function and L1 and L2 are real numbers, so just some numbers, then the statements, the limit as x approaches negative infinity of f of x equals L1, and the limit as x approaches positive infinity of f of x equals L2, denote the limits at infinity. The first statement is read, the limit of f of x as x approaches negative infinity is L1, and the second is read, the limit of f of x as x approaches infinity is L2. Some other things to note are if r is a positive real number, then we've got the limit as x approaches infinity of 1 over x to the r equals 0. And if x to the r is defined when x is less than 0, then the limit as x approaches negative infinity of 1 over x to the r equals 0. Now this all sounds quite complicated, as a lot of math definitions tend to. That's why we want to look at some examples and get an idea of what does this actually mean in terms of things that you'll be working with, whether it's in the notes or on the assignment, etc. So that's what we'll do here, is let's do some examples. Find the limit as x approaches infinity of 4 minus 3 over x to the power of 2. Well, from earlier, I've learned that I can break this up into two separate limits. I could say this is the limit as x approaches infinity of 4. Okay, and then I can do minus, or minus here, the limit as x approaches infinity of 3 over x squared. Well, I can also say that this is the limit as x approaches infinity of 4 minus, now I can think of this as 3 times 1 over x squared. And so then I'll say the limit as x approaches infinity of 3 times 1 over x squared. All right, so now this is the limit as x approaches infinity of 4 minus, now in brackets, I'll do the limit as x approaches infinity of 3 times the limit as x approaches infinity of 1 over x squared. Okay, now that I've got everything separated, what are all of these different pieces? The limit as x approaches infinity of 4, there's no x's here, so this will just be 4. Minus, in brackets here, this will be the limit as x approaches infinity of 3. There's no x's here to plug in, so then I've just got 3 times, and then my rule said if I've got 1 over x to the r, in this case, r is going to be 2, that goes to 0. So then this would be, this limit is 3, and then this limit is 0, so 3 times 0 here. Well, 3 times 0 is just 0, so this is 4 minus 0, or just 4. The limit as x approaches infinity of 4 minus 3 over x squared is 4. Here's another way to think of this. 4 minus 3 over x squared. As x approaches infinity, x is going to get very, very, very large. Larger and larger. So if I plug in x to x squared at the bottom here, then 3 over x squared, as x becomes larger, this fraction, 3 over x squared, is going to become smaller and smaller. Think of it as if I plug in 1, this would be 3 over 1 squared, or 3 over 1 is 3. But if I were to plug in, let's say 1,000,000, then 1,000,000 squared would be a really big number, but because that's in my denominator, 3 divided by that is going to be a very, very small number. So this is going closer and closer to 0. So then I would just have 4 minus this 0, just like I did here, would be 4. Okay, what about this one? Find the limit of x approaches infinity of 3 over 5 to the x, 5 times x to the 4th plus 7. So we can, again, break this up completely. And we can say this is going to be the limit as x approaches infinity. And I could say that the first part would be 3/5. We're taking out the 3 and the 5. Okay, times the limit as x approaches infinity of 1 over x to the 4th. Okay, that part. Then plus, now I'm going to do the 7, the limit as x approaches infinity of just 7. And then I could say this would be 3/5 because there's no x's there. 3/5 times 1 over x to the r, this time x to the 4th. That's going to be 0. And then plus the limit as x approaches infinity of just 7 would be 7. Well, this would be 3/5 times 0. Anything times 0 is 0. Plus 7 would be 7. So the limit of this whole thing, as x approaches infinity, of 3 over 5x to the 4th plus 7, this would be equal to 7. And I could break it up like I did, or I could kind of think about it just like I did at the end of the last one and say as x approaches infinity, x is going to get very, very large, which means that this fraction, 3 over 5 times a very large number at the bottom here, as x gets bigger, this whole fraction would get smaller and smaller, all the way down to approaching 0. So then it would be 0 plus 7, just like I have here, which is just 7. So that might be even a faster way to think about that, instead of having to break it up, completely like we've done. I also have limits at infinity for rational functions. Let's say I've got f of x equals n of x over d of x. So these are two different functions. I can think of this as one polynomial over another. And here, n of x might be something like a sub n to the x of x to the n plus all the way down to just a constant. And same thing for d with b's, and then instead of n's, m's. So what does that mean? So this is essentially what I want to do is I want to look at the leading term and look at the powers of that. X to the n for the top part, and then x to the m for the bottom part. If n is less than m, meaning if the highest power in your numerator is lower than your highest power in the denominator, then this whole limit will go to 0. If they're equal to each other, so if the highest power in your numerator is 4 and your highest power in your denominator is 4, so n is equal to m, then you want to look at the leading coefficients. How many of those x to the fourths do you have in the numerator? How many of those x to the fourths do you have in the denominator? If, let's say, you have 3 of them, 3x to the fourths in your numerator, and that's your leading term, and your denominator has maybe 5, okay, 3 over 5, I think I said 3 over here, then we would do 3 over 5 would be what your limit approaches. If n is greater than m, so if the leading coefficient in the numerator is larger than the leading coefficient, or the leading power, is larger than your denominator, the limit does not exist. Okay, so I've got that in my other words. Okay, if the leading power of the numerator is less than the leading power of the denominator, the limit is 0. That's what this first one is. If the leading power of the numerator is equal to the leading power of the denominator, the limit is the ratio of the leading coefficients. And if the leading power of the numerator is greater than the leading power of the denominator, the limit does not exist. Again, when I look at these definitions, they're kind of purposely written in a way that's really fancy and kind of confusing. So let's look at some examples and try to use this. Now, you might look at this and go, we don't have a whole lot of space here. And that's okay, because all I really need to look at is what is the highest power on top, what is the highest power on bottom. So here I've got the highest power on top is x to the 0, because I don't have any x terms on top. And the highest power on the bottom is x to the 1. So I would say 0 and then 1 on the bottom. Okay, so in this case, I've got the leading power of the numerator is less than the leading power of the denominator, so the limit is 0. I could just say that this whole limit, the limit as x approaches infinity of 3 over x plus 5 is 0. That's all you would need to do. Okay, for this one, I've got the highest power is x to the third on top. The bottom, I've got x to the first power. So the numerator, the leading power of the numerator is greater than the leading power of the denominator. The limit does not exist. So I would say just does not exist, or you could say DNE. Okay, limit does not exist. And really, what does that mean? It means as x approaches infinity, so as you go to the right, let's say, okay, this is just going to approach, f of x is just going to approach infinity. So it's just going to shoot up and up and up, further up. Okay, here I've got my highest power on top is 2. My highest power on bottom is 3. When the numerator, the highest power in the numerator, is less than the denominator, this goes to 0. So the limit as x approaches infinity of 6x squared over 3x to the third is 0. All right, here I've got a whole bunch of stuff. But remember, the first thing I care about is only what is the highest power. The highest power in the numerator is x squared. Highest in the denominator is also x to the second power squared. So when they're equal to each other, I look at the ratio of the coefficients. How many x squareds do I have in the numerator on top? 2. How many do I have on the bottom? 5. So then the limit as x approaches infinity of this whole thing, and I didn't look at anything else because I didn't need to, 2x squared minus 6x plus 11 all over 5x squared plus 5x plus 1. Nothing else mattered here. I just needed the powers, and then when they were equal to each other, the ratio of the coefficients. This will just go to 2/5. All right, and a couple more. Here I've got the highest power is on top, so this limit does not exist. And the last one like these, I've got highest power on top is 1, x to the first power. Highest power on the bottom is 1, x to the first power. So then I look at the leading coefficients. The ratio is 6 on top, 5 on bottom. So it'd be 6 over 5. The limit as x approaches infinity of the whole thing here, 6x plus 4 over 5x minus 7. This whole thing will go to 6 over 5. And so these problems look complicated when you're first starting out. But really, you can just do them as quickly as we did all of these examples. The next thing we'll do is look at sequences, because they're very similar. So how does the sequence work? Let's say I've got a sub n equals 1/2 to the n. What that's really saying is your first term, n is how many terms in you are. Your first term would be 1 over 2 to the first. Well, 1 over 2 to the first power would be 1/2. Then your second term, a sub 2, would be 1 over 2 to the second power. Well, that just means square the top, square the bottom. So 1 squared would be 2, 2 squared would be 4. Your second term would be 1/4. A sub 3, your third term, would be 1 over 2 to the third power. So this would end up being 1/8. Fourth term would be 1/16. Fifth term would be 1/32, and so forth. Okay, so this works very, very similarly. And so we want to look at where the sequence converges to, if it converges. And I can follow many of the same rules. Just if it doesn't converge, it's said to diverge. And one example of this might be if your sequence goes 1, -1, 1, -1, 1, -1, back and forth. This would oscillate, meaning the sequence diverges because it doesn't approach a unique number. So that's the key, is does your sequence approach a unique number? So you might get a problem like this. A sub n equals 2 times n plus 1 over n plus 4. Find the first 5 terms, and then find the limit. So if I were to plug in 1, this would be, let's see, the top part would be 2 times 1 plus 1. And the bottom part would be 1 plus 4. It would be 3 over 5 would be my first term. Okay, my second term, plug in 2. So it would be 2. Let's do it this way. just change this to a 2 here. And then change this to a 2 there. And I can see my second term would be 5 over 6. My third term would be 2 times 3 plus 1. And then that's over 3 plus 4. So my third term would be 7 over 7, or just 1. My fourth term would be 2 times 4 plus 1. That would be 9 over 4 plus 4. So it would be 9 over 8. Lastly, my fifth term, because it's only asked me for the first 5 terms, this would be 2 times 5 plus 1. So it would be 11 over 5 plus 4. 11 over 9. So what is this limit then? Is it converging somewhere? I could do the same thing where I could say, what's the highest power on top? This would be n to the first power. What's the highest power on bottom? This would be n to the first power. So they're equal to each other. And just like before, when you've got the highest power on top is equal to the highest power on bottom, I look at the coefficients. The ratio would be 2 over 1, or just 2. So then I would say the limit as n approaches infinity of 2n plus 1 over n plus 4, the limit of this sequence as n approaches infinity would be 2 over 1, or just 2. Okay, the next one. Find the first 5 terms of the sequence, then find the limit if it exists. Let's clear this. So the first term would be 2 times 1 plus 1 over 2 squared, then plus 4. So the first term would be 3 over 8. Yeah, the second term, now plug in 2, so it'd be 2 times 2 plus 1 on top over 2 squared. Oh, actually, I didn't plug in this one right. This one should have actually been, this should have actually been 1 squared. Plug in 1 there. I accidentally plugged in a 2. Then plus 4. This should actually be 3 over 5. Okay. The next one, though, let's just start over. 2 times 2 would be 4, plus 1 would be 5, over 2 squared, so that'd be 4 plus 4, so that would be 8. There we go. Third term, 2 times 3 would be 6 plus 1 is 7, over 3 squared would be 9, plus 4 would be 13. Fourth term, 2 times 4 would be 8, plus 1 would be 9, over 4 squared would be 16, plus 4 would be 20. And then the fifth term, 2 times 5 would be 10, plus 1 is 11, over 5 squared is 25, plus 4 would be 29. All right, so let's find the limit then. I could do the same thing where I look at the powers. The numerator is less than the denominator, n to the first power, n to the second power. So when the numerator is less than the denominator, the whole limit goes to 0. So I would say the limit as n approaches infinity of 2n plus 1 over n squared plus 4 is 0. These fractions would get smaller and smaller and smaller. Okay, last one. 2n squared plus 1 over 4n squared. First 5 terms again. So let's plug in the first one. So n to the second power. 1 squared would be 1 times 2 would be 2 plus 1. So I've got 3 over 1 squared would be 1 times 4. So that'd be 4. Okay, second one, let's actually do that in the calculator. So it'd be 2 times 2 squared plus 1. So it'd be 9 over 4 times 2 squared over 16. Okay, third term would be 2 times 3 squared plus 1. And then it'd be 4 times 3 squared. So 19 over 36. Fourth term, 2 times 4 squared. And then plus 1. And then at the bottom would be 4 times 4 squared. So 33 over 64. And the fifth term, 2 times 5 squared plus 1. And this is over 4 times 5 squared. So 51 over 100. Is there a limit here? Well, the highest power in the top would be 2. The highest power in the bottom is 2. So then I look at the leading coefficients, 2 over 4. The limit would go to 2 over 4, which is the same as 1/2. So we see 3/4, okay, is about 75% of, if you think of a circle filled in, and then this would get smaller and smaller and smaller, all the way down to 51 over 100 is almost half of a circle filled in. Right? So the limit as n approaches infinity, as the sequence, the terms approach infinity of 2 or n squared plus 1 over 4n squared would be 2 over 4, but that reduces to 1/2. Hope this helps out with thinking about limits as they approach infinity, as well as looking at sequences. Of course, if you have any questions, please let me know.